Hi. So today I'd like to go over quantum mechanics particle in a box problem to prepare you for our discussion of quantum dots. So if you've had modern physics, this should be a nice review for you, and if not, it'll be a nice teaser for when you take modern physics. So as a reminder, this is the Schrodinger equation, minus h bar squared over 2m times the second derivative with respect to the spatial coordinate of the wave function psi, plus the potential energy that the particle is bound by times psi is equal to the energy of the particle times psi. Now here, m is the mass, h bar is Planck's constant, 6.626 times 10 to the minus 34 joule seconds, divided by 2 pi. So h bar is h over 2 pi. And we're going to solve this equation for the simplest possible case of confinement. We're going to confine the particle in one dimension, only in the x, and we're going to confine it to what's known as the infinite square well potential, or affectionately known as particle in a box. So what is a particle in a box? Well, it's a particle, like I said, confined to a one-dimensional region of space, and basically it's just bouncing back and forth between two walls that are considered to be impenetrable, okay, which means that the potential energy at the wall and past the wall is infinite, okay? Now, this is going to give the same solution as the classical physics case for a standing wave on a string, like a guitar string or some other form of musical instrument, all right? Now, as long as the particle is inside the box, the potential energy isn't going to depend upon its location. It's just a constant value. We're going to choose, for the sake of ease, to have that constant be 0, okay? So the potential energy is 0 inside the box and infinite outside the box. This ensures that the particle is bound inside the box and cannot escape the box at all. Since the walls are impenetrable, there's 0 probability of finding the particle outside the box. Now, since the absolute value of the wave function squared gives you the probability of the particle's location, then what that means is that outside the box, that wave function has to be 0. Okay, so the wave function is 0 for x less than 0 and for x greater than L, where L is the length of the box. And so what that means is that to ensure continuity of the wave function also has to be 0 at those values. So at x equal to 0, the wave function is 0, and at x equal to L, the wave function is 0. Okay? So if we plug into our Schrodinger equation for the potential, remember we start off with this equation for Schrodinger's equation, minus h bar squared, d squared psi dx squared plus u psi is equal to e psi. But we're not going to even bother with a solution outside the particle, with the particle outside the box, because the potential is infinite and the wave function is 0. So we're just going to worry about the solution inside the box. And inside the box, u is equal to 0. So that means that that second term in that sum goes away, and we're just left with minus h bar squared over 2m times the second derivative of psi with respect to the spatial coordinate is equal to e psi, where e is the energy. Now, here is pretty much all of the first semester of differential equations summed up for you in one sentence. When you want to see if you can solve a differential equation, plug in a possible solution and see if it works. There you go. I've just saved you 4 months. I'm kidding. It's not that simple, but it's almost that simple. So we just have to think about what function that we can take two derivatives of and then get back negative constants times the function. Because if you look here, if we rearrange this differential equation, we'd be taking two derivatives of our wave function psi, and then we'd be getting back minus 2me over h bar squared times the wave function again. So we're going to get back some negative constants times the wave function. Well, there's only a few functions that I know of where you take two derivatives and you get the function back again, right? There's exponentials and there's trigonometric functions like sine and cosine. Now, if you take the derivative of a real exponential like e to the ax or e to the minus ax, you're going to get back a squared times e to the minus ax, right? So you're not going to get back negative constants times your exponential as long as your exponential is a real. So that means that we're stuck with our sine and cosine functions, or our imaginary exponentials, which, let's face it, are sines and cosines anyway. So if you take two derivatives of sines and cosines, you're going to get back negative constants times the sines and cosines again. Now I'm going to leave it as an exercise to you to plug it in and make sure that this works. Okay, I'm not going to demonstrate that, but I'm going to make my guess that psi of x is going to be a sum of sines and cosines. And I'm going to leave the constants undetermined for now. So I'm going to have a sine kx plus b cosine kx, where k is an undetermined constant and a and b are also undetermined constants. Now, I know this works. You can prove it on your own. But let's go ahead and apply boundary conditions to this function. The boundary conditions are that the wave function has to be 0 at x equal to 0 and x equal to L. Now let's apply the x equal to 0 one first, because that's the easiest one to apply. We know that the wave function has to be 0 at x equal to 0. So if we plug that in, then a sine of 0 would just give you 0, so that's 0, so that's good. But if you plug in x equal to 0 to the cosine term, you're going to get b, right? Because the cosine of 0 is 1. So that would mean that psi at x equal to 0 is equal to b, and that would mean that b equals 0. Okay? So that cosine term goes away, and we're just left with the sine term. Okay? Now remember, k is a generic guess here, but we know from our sines and cosines that k is going to be the wave number, which is 2 pi over lambda, to make the argument of the sine and cosine dimensionless. If you're a little confused about what I mean by that, just quickly look it up in any introductory physics book and you'll see that what I'm saying is true. Okay, so k is our wave number and it's equal to 2 pi over lambda, and it's a generic undetermined constant, which means that we don't know what our wavelength is yet, which is fine. All right, now let's plug in to our solution that's remaining. Psi of x is equal to a sine of kx, and let's plug in for the remaining boundary condition, and that boundary condition is x equal to L. So we know that at the boundary x equal to L, psi has to be equal to 0. So we have a times sine of KL equals to 0. Now we could say that a is equal to 0 too, but that would just mean that the wave function is 0, and that's not very interesting. So let's instead say, when is sine of KL equal to 0? Well, the sine function is only 0 when the argument of the sine function is a multiple of pi, like sine of pi is 0 or sine of 2 pi is 0, and so on and so forth. So what we're going to have to do is solve for what our undetermined constant k is. K times L would then have to be equal to some integer value n times pi. So if we solve for k, then we know then that k is equal to n pi over L. And we also know that k, just by definition, is 2 pi over lambda. And so that tells us we can simply solve for what our wavelength would have to be, and we end up with lambda is equal to 2 times L over n, where L is the length of our box and n is some integer. And this has to be true in order to satisfy those boundary conditions. So what would our wave function look like? Well, we still haven't determined a, but we don't really need to kind of graph in a generic way what this would look like. And this is what it would look like. So for n equal to 1, our wavelength would be 2L, okay? And so we see only half of a sine curve here. And then for L equal to 2, for n equal to 2, we'd have L as our wavelength, and so we see the full sine curve fitting in there, okay? And then it would go so on and so forth up with a number of bumps there, and our sine function increasing as n increases. So that n equal to 4 would have 4 bumps, and so on and so forth. So this is our wave function. Now we know that the probability of where the particle is located is related to not the wave function, but the absolute value of the wave function squared. So if we graph that next to it, then this would be sort of our probability density function, if you will, for a particle in a box. Okay? So we've got infinitely many solutions here, basically, a set of infinite solutions. Now, this does look exactly the same as classical waves on a string, the solution for that. And so that is, if you pluck a string or give it a little wiggle and excite it, and you confine the string and hold it at both ends, then standing waves are going to form in the string. You should have covered this in your introductory physics courses, but if you need a review, I provided a link to a hyperphysics website here, which also provided these groovy little pictures, and you can get a review of the classical standing waves on a string. And this is how musical instruments, for example, like guitars work. If you want to change the pitch of the note, for example, you would move your finger to a different set of frets, changing the length of the string, which would change the wavelength of the standing wave, which changes the frequency of the pitch that you hear when it comes out. Okay, continuing on, let's solve for what our energy values are. So we can do that by plugging in our wave function, which we know now, a sine kx, into this little differential equation and solving. So if we take two derivatives of a sine kx and then multiply it by minus h bar squared over 2m, then we get minus h bar squared over 2m times minus k squared times my wave function again, and then that's equal to e times my wave function. So now I can pull out the wave function from both sides. I can plug in for what I know k is, where I solved for it on the earlier slide. K, remember, was n pi over L, so I can plug in for k into that equation, and I can end up with my energies. My energies for my particle in the box are going to be equal to h bar squared times n squared times pi squared over 2ml squared. Remember, h bar is Planck's constant divided by 2 pi. N is our quantum number, okay, that integer value starting at 1 and going up from there. And m is the mass of my particle, and L is the length of the box. I can plug in for h bar equals h over 2 pi and get an expression just in terms of Planck's constant if I want. You see both expressions kind of interchangeably. If I do that, then I get h squared n squared over 8ml squared, okay? And those two expressions are equivalent, all right? So those are my energies for that, okay? Now, we chose the potential energy of the particle to be 0 inside the box. So if you want to figure out what the mechanical energy is, remember the mechanical energy is defined in introductory physics as being the kinetic plus the potential energies. If the potential energy is 0, then that means that the total energy is just the kinetic energy. So this means that our particle inside our square well has a kinetic energy of h bar squared, n squared, pi squared over 2ml squared. Now look here, this energy is discretized. N can equal an integer value, so it's going to be h bar squared pi squared over 2ml squared times, and then 1 squared, or 2 squared, or 3 squared, or 4 squared, and so on and so forth. This kind of gives rise to the name energy level for what N means, okay? Because instead of a continuous spread of energies, now we have discretized values of the energy, and it's convenient to think of the energy going up in steps called levels, right? So the energy level is sometimes the name given to that number N, which is also called the principal quantum number for this particle in a square well potential. This is what the energy levels look like. Usually we refer to the ground state for the n equal to 1, we call it the ground state, and then from then on we give it name like first excited state for n equal to 2, second excited state for n equal to 3, and so on and so forth. So your ground state would be, we'll call it E1, because it's n squared as you go up, then the second level would be 4E1, and then 9E1, and 16E1, and so on and so forth, or n squared times your ground state value. Notice that the particle is not allowed to have a kinetic energy of 0. This is very non-classical, but it happens a lot in quantum systems. Now also remember that our wavelengths are restricted to specific values, that lambda is equal to 2L over n, where n is our energy level or quantum number. Therefore, what that means is if we plug into the equation for the de Broglie wavelength, lambda is equal to h over p, and we rearrange and solve for our momentum p, being h over lambda, then we can solve for what the momentum values are. So when we plug that in, we get p is equal to nh over 2l, okay? Now, if we squared that, p squared divided by 2m, we get back our energy again, because remember, our total energy is just our kinetic energy, and 1/2 mv squared, or p squared over 2m, is our kinetic energy. So this momentum value, this is our absolute value, and it can be positive or negative for left or right motion, depending on which way it's going. The particle is never still, though. It's always bouncing back and forth with that momentum. So that's the particle in a square well, or particle in a box. Hopefully that was a nice review for you, and I'll see you next time.